Hello all. So here is our notes on circular motion. Okay, so we've been doing stuff moving in a line for now, right? We've been doing stuff moving in nice horizontal lines like this. So now we're going to be talking about what happens if we have an object moving in a circle or a semicircle or something like that. So some things to keep in mind. If we talk about the frequency, that is the idea of the number of cycles over a specific amount of time. So let's say I go around this circle 1, 2, 3 times in 30 seconds. My frequency would be 3 over 30, which would give me a frequency of 0.1, and the unit is a 1 over a second, or as it's better known, a hertz. Okay. The period, on the other hand, is the time for a specific amount of cycles. Okay, so for the same example, our time was 30 seconds. The number of cycles was 3. So we have a period of 1 second. And what that means is the time to get around the circle is 10 seconds. So like the time to complete one loop. Okay, and then the last thing to talk about, remember the circumference is the distance around a circle, and we can calculate it by doing pi times the diameter, or the way you're most likely going to see it written is 2 pi times the radius. So remember, the radius is the distance from the center outwards, and the diameter is just twice that. Okay. An important distinction is between speed and velocity. Remember that speed is a scalar, and it is a measure of how fast you are going. So your speedometer reads or tells you how fast your car is traveling. Velocity is a vector, and it is how fast you're moving in a specific direction. And it's really easy to remember the difference between the two because velocity and vector both start with V, speed and scalar both start with S. Okay. So when we talk about things moving in a circle, we often talk about them moving at a constant speed. Okay. So think for a second about why we can't say these things are moving at a constant velocity. Remember, we're moving in a circle. So speed is how fast we are going. Velocity is how fast we're going in a specific direction. So if you're thinking we can't say constant velocity because we are always changing direction, you would be right. And you can quickly prove that to yourself by standing up and spinning in a circle. So feel free to do that now. You just stand up, and when you spin around in a circle, you'll notice that what you see or what part of the room you see changes as you spin in a circle. That means the direction you face changes. Okay, so to find that constant speed, and the videos talked about this a little bit, we start with the idea that velocity is a change in distance over time. But we're moving in a circle, so we need to use the circumference over the time. Okay, this is an equation that you do need to remember because it is not on your reference table. Okay, now for representing the velocity or the direction of the velocity. Okay, so if we have an object moving counterclockwise, at any point along the circle, we say the velocity is tangent to the circle. So what that means is it creates a 90-degree angle with the radius and also touches the circle once and only once. Okay, so it's tangent to the circle. So these arrows represent the velocity at any given point. So the velocity at any given point will have a magnitude equal to this equation and a direction based on the direction the arrow points. Okay, now remember, we have this idea of inertia. Okay, and inertia says an object is going to keep moving in a straight line unless a force acts on it. So if I let the object go at this point, okay, the object is going to continue flying along that red dotted line. So that's also what the velocity vector could represent for us, is the direction of the object is going to travel after or if it is let go. So moving in a circle, are the objects accelerating? Well, if we remember, acceleration is defined as so acceleration is a change in velocity over time. Okay, and we have a change in velocity for objects moving in a circle because we have an object that is constantly changing direction. Okay, so the acceleration for any object traveling in a circle, okay, no matter where it is, that acceleration is always going to point inward. Okay, and we give this acceleration a specific name. We call it centripetal acceleration. Okay, so I think that centripetal sounds like center pull. Okay, in Latin that actually means center seeking. So that's how an easy way to remember what direction the acceleration points. And you'll notice that I'm representing the acceleration with an A subscript of C. That is true on all of your reference tables. You'll see it as an A with a subscript of C. You can think of that C as meaning circle. So because it's the direction of the velocity that's changing, we can't use the standard A as change in velocity over time. That doesn't work for us. Okay. So to calculate the centripetal acceleration, again, AC for circle, we need to do V squared over the radius. Okay, so sometimes that might mean we need to do the 2 pi r over the period squared over the radius, or sometimes we're just given the velocity and the radius and we can just calculate it. Okay. So do objects moving in a circle have a net force acting on them? Well, we know from last unit that net forces cause acceleration. So even though we're not accelerating in the traditional sense of speeding up or slowing down, we are still accelerating. So these objects do have a net force acting on them. Okay. So we're going to consider this a new net force. So instead of writing some of all the forces in the x or y direction, we're going to think about forces in the centripetal direction, and they're going to equal MAC. Okay. Now, the centripetal force is not really what's causing the object to move in a circle. What might cause a centripetal force is something like gravity. So we could set Fg equal to MAC. It might be a friction force, right, if we're moving in a circle. So that would be an example of like a coin on a turntable and the coin's not moving, or a tension could cause a centripetal force. It might be a little bit of like a normal force and gravity causing us to move in a circle. We're going to talk more about those kinds of problems tomorrow. Okay. So our base equation is the same net force equation that we've been doing. Okay, it's just this left-hand side gets filled in with those different forces. And again, this MAC is really MV squared over R. Okay, so the direction of the force. Now, the centripetal force is a net force, which means it's going to share an a direction with the acceleration. So if our acceleration points inward, then our centripetal net force, so I'm going to write this as F net C, must also point inward. Okay. So there could be multiple forces acting on the object at a given point. So let's think about a roller coaster loop-the-loop, right? At this top point here, there is a normal force pointing down from the surface that's right here, and a force of gravity. And both of those forces combine to give us that net centripetal force, or the MAC. Okay. So on a free body diagram, you wouldn't necessarily draw an arrow like this. You would draw them like this, with the actual forces causing that centripetal acceleration. Okay. Now, one thought question you might be thinking of is think about driving around a circle in your car, which way does your body tend to lean? Or think of like the scrambler ride or anything like that. Do you fall into the circle or do you fall out of the circle? So are you pushed outward or kind of pulled inward? Okay, so think about it for a little bit. Maybe discuss with your neighbor. Now you're probably thinking that like, oh, well, I'm definitely pushed outward. Okay? So how is this possible given the centripetal force? Remember Newton's first law. So Newton's first law says that any object wants to move in a straight line unless acted on by a force. So when you are driving around this circle, so here you are, okay, what your body wants to keep doing is moving forward. So instead of continuing on with the circle, it just wants to keep moving forward. All right. But we have this force acting on us, pulling us into the circle, specifically into the center of the circle. So that's center seeking or centripetal force. Okay. So the reason why you feel like you are falling outward is because of your inertia, and then the force causing you to move in a circle acts on you and pulls you right along in the circle with you. So there's no force actually pushing you outward. It's just your own body's inertia. So it's just that first law thing. Because you have mass, you want to keep moving in a straight line. The car or the scrambler ride or whatever is acting on you says, nope, I'm going to pull you in towards the center, and you keep moving in a circle. And that is it for the basics of centripetal or circular motion, centripetal acceleration, and centripetal force.